past and to make most use of the time. We'll start now. Thank you very much. Thank you very much for joining today's talk. My name is En Vanal. I'm with the Vehicular Technology chapter in Victoria. The talk is co-sponsored by our IEEE Communication Society chapter, headed up by Dr. Golna Homeimi, who is online today. The talk's part of a 4-talk international set in Auckland, Melbourne, Sydney, and Singapore. And it was to be face-to-face, but international travel connections conspired against us. The title of the talk is Vehicle-to-Vehicle Communications for Uncrewed Aircraft Systems. Our speaker is Professor Kamesh Namuduri, who is Director of the Autonomous System Laboratory at the University of North Texas, which I believe is located in Denton, which is located in the Dallas-Fort Worth Metroplex, I think. Prof. Namuduri is one of the authors of a book entitled UAV Networks and Communications, published by Cambridge University Press. He is also leading the Smart and Connected Community project on deployable communication systems. Can I welcome, on behalf of all of us, Professor Namuduri? Thank you.
Thank you, and for the wonderful introduction. It's nice to meet you virtually. I'm going to share the screen. Then, so thanks to the VTS and Communication Society section of Victorian section. This talk is about vehicle-to-vehicle communications for unmanned or uncrewed aircraft systems. I'll try to keep it at a high level, at the same time point out some what you call fundamental research elements within these topics. So I would like to thank IEEE, the National Science Foundation, and NASA for providing the support for the research. So I'll briefly talk about UNT, and then also just for the context, advanced air mobility, and specifically the need for V2V communications. And then talk about the 5 use cases that showcase the real-time need of V2V communications. Also, the same 5 use cases are being used by standards organizations like RTCA, GAMA, and of course IEEE to come up with the protocol, V2V communication protocol. And then I'll also refer to RTCA, ASTM, IEEE. These are the organizations that are actively working on this topic. And then it is supposed to be 1920.2 and 1954. Those are 2 active standards that are currently looking at this topic. And then we'll talk about, how does the future look. So these are my students. Thanks to all of them, everyone in some sense or other, they contributed to this research, and some of these figures actually come directly from their work. And interestingly, all students except the 3 PhD students are graduating this semester. So I have an unusual situation of having a nearly empty lab other than the PhD students. So I need to recruit more in the next year. All right. So this is a depiction of what is going to come in advanced air mobility. You can see multiple types of vehicle, like multiple sizes, and then they're all sharing the space, sharing the same airspace, which is a bit challenging. So at one end, in one direction or one dimension, small vehicles, for example, the city where I am right now in Dallas-Fort Worth and many other cities, there are initial attempts to initial plans rather, or initial projects that are ongoing to deliver small items. For example, in my area, some of my students ordered a burger, like which instead of going to the shop and picking it up, they ordered to just see how it is being done. So the vehicle, small vehicle, probably travels for 15-20 minutes at most, and then it will fly at 400 feet, around 400 feet. And then from the at certain height, maybe come down below 200 or 200 feet, and then drops that item in your in front of the, or within the lawn, in the front yard. So these are the things that are ongoing. And more interestingly, as of now, in Dallas-Fort Worth, there are several companies trying to get the market. So what they're trying to do is they reached out to NASA and asked them to help them, rather to help to share the space, and try to help them in terms of deconflicting, because each company will have its own services, but then there should be a way to avoid any potential conflicts. So in that, to support that, NASA created what you call key sites, and Dallas-Fort Worth or North Texas is one of the key sites where all this experimentation is going on. Remember, this project is called UTM. UTM stands for UAS Traffic Management. It is common. In fact, these names are consistent across the world. Maybe sometimes in some places they're called global UTM. So UTM as a project that started in around 2015, around that time, but now it is sort of matured and the real world applications are coming out. But still, there is some more work to be done. So the next level is advanced air mobility or urban air mobility. So this in this project, the flights can be flying around up to 4,000 feet. So it's like 400 feet UTM flights, whereas the AAM flights fly about 4,000 feet. So the vehicles are going to be like taxis, ambulances, large cargo delivery. These are the things. So we expect to have longer flights, a longer duration. Then at the same time, you also see that both the UTM and AAM or UAM have to coexist. And obviously, the airspace cannot be unique, or we cannot find separate airspace for UTM and AAM. Even the regular vehicles, like commercial vehicles, like helicopters, even the big flights that Delta and all those big flights also, at some points, they have to share the space, especially at the airports. A typical scenario is like in metropolitan cities, from a suburban area to downtown or maybe to the airport, we expect to see these vehicles flying. So short trips, like probably 15, 20 minutes, maybe 30 minutes. Then obviously you need some takeoff and landing spots. So if you look at the symbol M in the picture, that's typically we call that, you can call that as a vertiport, or some rooftop where vehicles are going to take off and land. Obviously, there's a lot of infrastructure needed. We're going to talk about that. So this is the scenario, a depiction of what is going to come in near future. And by the way, FAA in the US released a document called Innovate 28. The Innovate 28 is like a plan to implement advanced air mobility within 5 years. It started actually, it was published in 2023. So the idea is by 28, at least in some major cities, the NASA wants to see this realization of advanced air mobility. In fact, since one of the professors talked about autonomy, in fact, I'm also working at autonomy. Autonomy is the central theme going forward. So far, there were some initial trials, rather field trials, to test autonomous airspace operations. But going forward, in the second phase of advanced air mobility, we call that as a national campaign. we are going to see more and more of autonomous operations, autonomy. Also, in the initial phases, FAA wants to see a pilot on the unmanned aircraft system. Even though we are flying unmanned systems, which are readily available, actually, the platforms are readily available. Companies like Joby, Archer, Whisk, these companies, Lilium is another company which is actively pursuing eVTOLs. So these vehicles are ready to fly, but what is stopping us to fly them now? Or to use them for real-time services, the need for regulations and safety and security. Those are the things. So we need to do a lot more testing. But pretty soon, this is going to be, we're going to see them in action. Okay. And now let's come to the V2V communications. Why is this so critical? You will see more reasons in the next few slides. But this picture actually coming from RTCA, one of the standards organizations, which developed the use cases and sort of a minimum requirements. These are the things that RTCA developed. And they're also looking at spectrum. Spectrum is one of the key elements for this. So what spectrum or what frequency band is good for V2V communications? So these are still being discussed, actually. Somehow the RTCA is took a break in continuing this work on V2V. But from IEEE point of view, we started this work on V2V way early, actually, before even the industry picked up. So we started this work in 2017, really. So what do you mean by V2V? Online, air-to-air communication between vehicles. It is coexisting with other types of communication. So one interesting dimension is V2V doesn't mean that it's just only V2V. It's V2V has to include, V2V includes air to ground as well, or air to air communications has to include air to ground communications as well. There is one thought, some people are suggesting the frequency band should be different for V2V and V2 ground or air to ground. The reasoning is that they want to separate them for security reasons. It's still it's a point of debate, and it's a point that people are debating. Should we separate the frequency bands? Why not? Or can we keep the same? But in general, V2V should kind of, in some sense, has to include V2X and V2 ground. So you can look at other kinds of communication here, like ADSB, transponder, and then you also see the connection with the ATC, even though air traffic control is not going to manage advanced air mobility or even UTM, but we need to be connected. For example, there is a system called Flight Information Management System. It's pretty common, it's a universal around the world. So that system has all the data related to commercial traffic. So advanced air mobility systems or traffic management systems have to be in touch with FIMS. They should be connected so that, in case there is a conflict between a drone or this eVTOL or advanced air mobility vehicle with a commercial vehicle, they need to be resolved. And obviously there is a need for radar to detect vehicles that are not equipped with V2V. So we can't assume that all vehicles are going to have V2V or vehicle-to-vehicle communication capability. So we need to keep in mind that things like a rogue drone, for example, or even there might be birds, or there might be some other illegitimate or vehicles that are not supposed to be there. So if there is no communication with the other vehicle, then radar becomes very critical. So basically, this is a picture that RTCA depicted to highlight different, specifically V2V communications. And then going forward, you're going to see more information. So there are this work that I'm currently working on is not only theoretical. In fact, I'm being inspired by real world scenarios. So even though the advanced air mobility is a project for the industry, I started working on this project very early from the inception. And then at this point, I've been involved in 3 what you call phase 2 small business innovation research projects with startup companies, and each with $1 million or more. Then from the university, through university rather, I got several grants. One of them is National Science Foundation. This is called Resilient and Intelligent Next Generation Networking, or RINGS. We are in the 3rd year right now. And somewhat in a different context or on a different topic, high volume manufacturing and supply chain logistics. This project is funded by NASA. And then the state government also is providing some funds. They require kind of a cost share, but still they are very helpful in supporting these projects. And then a couple of standards. Standards take a lot of time, as we all know. So 1920.1 nearly took about 4 years to complete, but it was released in 2022. It gives a overall framework of airborne networking. But then, we need to create separate what you call standards from the overall framework. Like, for example, security, V2V communication. These are stemming from the parent project, if I may call, from 1920.1. So 20.2 is specifically on V2V communication, and we have almost finished it, and we expect to be at least release the draft by end of this year, and definitely by early 2025 it will be public. So there are other projects also, patents and startup companies. These are all pretty. They're going very well. The most interesting thing that I enjoy is students are able to get to work on these projects in the real world. And as I said in the beginning, all my undergrad students got the jobs, and they find the jobs lucrative, and then instead of pursuing masters, they're choosing the industry. But it is fine, and they will be, hopefully they'll come back and do masters and PhDs later. So now there are many topics within advanced air mobility, starting not only communications and traffic management, security, privacy. The interesting thing is the success of advanced air mobility depends on the community acceptance. Unless the community sees the value, for example, a layman or naive person might think, these are all spying on me. So we have to work towards educating. It's our responsibility to make sure that the community sees the value and adopts them. So they should help us. All the cities, for example, or municipalities, they have to help us to provide space, for example, to construct the vertiports. And by the way, vertiport is like a helipad, typically a 2-story building. I'm kind of interested in engaging with vertiport construction and engaging with vertiport, because from UNT, we are also looking into the behavioral aspects. For example, what is the stress load? What is the load on the pilot? And what's the difference between remote pilot and a commercial pilot? And then how many flights one remote pilot can handle? How many hours the person can work? So these are kind of new topics. Interestingly, every topic we look into, whether it is communications, security, privacy, autonomy, all these are there in another time in other areas. Like, for example, V2V communications is there already on the ground, but it is important to note the differences. High mobility is one big factor. Things like Doppler effect might come in, which may not be so significant, which is not significant on the ground. But when it comes to high mobility of airspace or air vehicles, coupled with high frequency, if we go for example, a millimeter wave, then Doppler shift is going to be significant. So to highlight, so one of the problems that I'm looking at is OTFS modulation technique. OFDM ODM is very standard, but going forward, probably OTFS might become a good candidate. OTFS stands for orthogonal time frequency space modulation, and a lot of work has been done in this. I'm also looking at for space communications. So this slide depicts the simple differences of what is air ground, what do you need for air to air. So command and control and navigational guidance, traffic management, you typically use air to ground communications or vice versa. But more specifically, we need air to air communications for what you call tactical deconfliction, or sometimes we call it operational deconfliction. So imagine two vehicles are so close and there is not even time to have talk to the ground and get any approvals. So in those cases, the time latency becomes very critical, and then to avoid immediate collision, we need to have this two-way communications. For example, one vehicle can say, "Oh, I go left and you go right, I go down and you go up." These are the typical maneuvers that are done in the military. So the same way, or even in commercial aviation. So those kind of protocols have to be incorporated into advanced air mobility. And given the lower altitude, even though we say advanced air mobility vehicles are going to fly at 4,000 feet, or roughly about 1.2 kilometers, but the height is not so much. You don't have so much of leverage. Same way, the distances will be very small, as compared to commercial aircraft. So given this kind of differentiation, we need to have more effective low latency and highly agile and adaptive communications. In fact, I'm not even, this talk is, we're only talking about the protocols, but there is a need for, like, for example, phased array antennas, beamforming and beam steering, to make sure that you always have a line of sight between the vehicles when they're communicating. So these are all, many people are working in those areas. Okay, so in terms of facilitating the traffic, one way to look at that is create some sort of lanes, corridors. In real world, the tracks are not going to be so straight and so clear, so clean, because it depends on the terrain. The altitude at which vehicles are going to fly will be different for different cities. But for academic point of view, it's always, it's a good idea to start with this kind of structure. So I call them as structured airspaces. So think about, like, these are all cells. Well, let's call them as air cells. And you're basically you're creating this structure in the airspace. These are all fixed, by the way. These are all, you can give a numbering, cell 1, cell 2, and of course you can give the direction. So for academic purposes or research purposes, I asked my students to think about like 200 meters as a size of the length of the cell. So this kind of structure is very meaningful, at least to do research from a mobility point of view or control point of view. But then communication folks came up with another structure. If you look at the literature, there are two professors that I know that who worked on communication, like related what you call cells in the airspace. They came up with the structure of what you call octahedron. It's called truncated octahedron as a meaningful or a useful structure or geometry. It is something similar to hexagon on the ground. The way you divide the region, or geographical region into like tiling in the ground for terrestrial communications. In the 3D space, they suggested truncated octahedron is a very suitable for frequency reuse, free cell, for concepts of point of view. So this work that I did in 2021, here I presented air corridors, concepts, design and simulation, and rules of engagement. It was published in Sensors. So if we can do this, and if you are able to divide the airspace into cells and then create these tracks, it's very meaningful because you can replicate this airspace on your computer and then ask questions like, okay, how many cells are occupied? How many vehicles are there in the airspace? And how much is the traffic? And in fact, you can also include for every cell the weather information. How is weather in each of the cells? So does that gives you a better handle on the traffic management. For example, if it is windy, in fact, yesterday I was at the airport. The wind was so high, and the wind speed was so high that people are being pushed on the ground actually. So if the wind is rough or the wind speed is high, then you can increase the spacing so that there is more space between vehicles. So you, for example, you can simply say, oh, let's maintain 2 cells spacing, two cells between 2 vehicles. So that way you're reducing the traffic, but you're giving more room for mobility. And then you can also see, traffic volume. You can control. You can make some changes, and in some sense, you can introduce what we call flight rules. In fact, flight rules cannot be designed by academicians. It is supposed to be done by the federal aviation organizations, but we can at least provide some idea. We can provide the framework to implement that kind of flight rules. Anyway, so here is another depiction of the need for vehicle-to-vehicle communication. So this is a paper that was published recently. Even though we use the diagram in one of the IEEE VTS VT magazine articles, especially shown advanced air mobility. So this picture depicts a scenario where a fleet of vehicles are track on the lane rather. So if one vehicle detects airspace hazard. So hazard is something like maybe like a flock of birds or a cloud, a thick cloud through which the vehicle cannot pass through. Or suddenly there might be a no-fly zone in a given area, depending on the events on the ground. So the cloud structure that I depicted here is like an example of airspace hazard. So if the first vehicle detects that, then we need to not only send this information to the rest of to other vehicles that are following in the same lane, also to the ground. So this is again another reason why V2V cannot exist on its own. V2V should be supplemented or complemented with the vehicle to ground communication as well. So detect and avoid strategies, for that we need, and that's one use case as you see from here. Then I'll show you a simple demonstration, simple simulation here. So look at that. This is an example where that shows, if you provide the proper V2V communication, then traffic can be managed. This is the simulation is fast, but you get the picture. So you can create. So what this is showing you is in the airspace, we can actually create these structures like intersections. In fact, some of my students have worked on something called a roundabout, another intersection. I'll try to show a simulation at the end. In fact, I showed the same simulation in the first talk. All right. So the simulation is right here actually. So this is a depiction of a roundabout, and look at if fleet of vehicles are passing through, then it is possible to negotiate for merging, requesting vehicles in the lane to make space, or and come up with some sort of a guidelines like like in the roundabout, in the intersection, there can be only one vehicle, maybe 2 vehicles. You can make up those kind of rules too. So this paper is going to be presented in ICC 2024. It's going to occur in June. All right. I also briefly talk about the standards. In 1920.1, the scope is defining a framework for self-organized ad hoc aerial networks. So even though we talk about ad hoc networks, a truly ad hoc network is nearly impossible. And there were some papers, some research studies showed that, especially with air vehicles, you can create ad hoc network. However, maintaining that will be very challenging in the sense there will be a lot of disconnections. And so given that, the general suggestion in the literature is that ad hoc network, especially aerial ad hoc network, should be supported through some infrastructure. At least, there should be one satellite link, a link to the, or maybe a cellular link. They will help to make the network stable. The other thing is industry, of course, the cellular industry, 3GPP is working very hard to support non-terrestrial networks for drones and even satellite. So they're all included in starting from release 17, if I'm right, 17, 18, 19. There is there's a focus on non-terrestrial networking. But the challenge with that is you cannot put cell towers everywhere, especially in rural areas. It's not possible to have cell towers everywhere. If you go for the alternatives are satellite communications with LEO, for example, but then handover management with LEO is kind of challenging, as we all know. So the standard as for 1920.1 focused on creating a framework. In fact, it's agnostic to any specific radio. It focused more on the data exchange, establishment of a network, addressing scheme, and then security. It provided a big picture, but it's not really ready to implement. It's not ready to, you can't just use the standard to go and implement. It requires, we realized that, and then started working on different parts. Like, for example, 1920.2 is an outcome of this support. So that's about V2V. So V2V communication, once again, we try to keep it agnostic to radios, in the sense, whatever frequency band you use, it should be okay, and it should be applicable for large vehicles or small vehicles. Of course, it requires some swap. It requires some payload. So the radios may not be able to carry them on a small drone, but a typical aircraft, especially AAM vehicles, should be able to do this, should be able to carry the load. So the focus again is on the information exchange. What kind of information we need to share? So it's like standardization of the information exchange rather than any other aspect. So I'm serving as the chair for this, and it is going pretty good. There is another standard that we started recently. The chair is Fabrizio Granelli from Italy. So this work is again outcome or a follow-up on 1920.2. The focus again is on aerial networking, but this time we're trying to make it agile, adaptive. And this is interesting because this goes into maybe potentially beamforming, beam steering concepts as well. Yeah. So please take a look at this 1920.2 and 1954. This new standard is started last year. Is 1954. All right. I want to show you this picture to put in perspective. So there is satellite communication, and within airport, you may know Aeromax is a standard for communication at the airport. Then the air-to-ground communications, and we have this LDACs, I think 1 and 2. So air-to-air communications, which was missing at the time. This paper was this picture is from a paper that was published in 2017 or so. All right. And over the air communications between aircraft is really required for these reasons. One is if you have a radio line of sight from the ground, that's well and good. But if it is not, then the very quick use case is how do you relay information beyond radio line of sight? You could think about other options like ADS-B or satellite communications, but none of them come close to what we are trying to do here: direct air-to-air communications. Okay, here is another reason, when I started this work, I read a paper from ICAO, International Civil Aviation Organization, and these are the words they used. Even also went to some of the meetings with the Aircraft Pilots Association at that time, and I was wondering why there was no direct air-to-air communication between commercial vehicles. For example, naively, I was asking, can't a pilot pick up a phone and call the other person, other pilot? It seems like it obviously, for example, through satellite communications, it can be done, or you can go through traffic control. But until that Malaysian aircraft missed or lost in the space, there was not the focus was not much on the air-to-air communications. So as of now, even after so many years, there is only one thing that FAA, for example, in the US and even other countries, made a rule to mandate every aircraft to have ADS-B is one thing. Then the new rule for drones is remote ID. So basically, a remote ID is a broadcasting of location, heading, speed, and those basic parameters. But that's it. And V2V communication has started. The efforts on V2V communication started very lately, but we still have a lot more to do in terms of facilitating this. All right. So you can see that three paradigms. You can use satellite communications, given that LEO satellites are becoming very popular, very useful rather, despite the challenges that of handover management is still a challenge, but at least we have we see a lot of work that is going on in the LEO satellites. And then cellular world is cellular net service providers are also actively working, but having a direct V2V communications is still very powerful, very useful, and it should be it's complementary to both satellite and cellular. Okay, there are things that we need to worry about in down the lane. For example, interference management, and of course handover optimization. These are the things that we need to focus in terms of fundamental research. You see that interference is larger rather at higher altitudes. So this is sometimes it's counterintuitive, but this is a big thing that we need to worry about. Okay, now I'm going to talk about the 5 use cases or 6 use cases that we developed. Now, these are some new ideas. You might see some ongoing work as of now, but in my group we focused on during the last 2-3 years we focused on this for 2 reasons. One is to develop a standard. I think the starting point has to be use cases, and then the approach that we are following in 1920.2 is you start with the use cases, but make the protocol or make the messaging and all that agnostic to use cases. So it is kind of interesting. You start with use cases and then basically say, oh, now we don't need them. And another way to look at it is, okay, start with, let's say we took 5 use cases, and these 5 use cases came from RTCA. A couple of them are same actually, even though I listed 6 here, but actually we have only 5. So start with those 5 use cases and then develop the messages and then the protocol. And later you see if someone comes with a new use case, whether the given messages and given protocol supports the new use case. If not, improve maybe add another message, maybe another field. So one thing that we are trying to do is we started with this what we call collision avoidance, separation, collaborative sensing, and information relay and rerouting. But then explicitly or for intentionally, we did not include search and rescue use case. So what we want to do is once we develop this standard, we want to see whether the same standard is applicable or can be applied for search and rescue. And then we also want to come up with a sort of a competition. We want the students or practitioners who are working in this area to use the standard for a new use case and give us feedback. So this is going to happen very soon through IEEE. So anyway, now let's get into these 5 use cases quickly. So one of them is merging. Merging can happen in many scenarios. One is you're changing the lanes. Maybe you're taking a turn and 90-degree turn, and then you have to merge. The other use case is when we are about to take off, and then you go up to certain height, certain altitude, and then join the traffic. So remember, we are considering here what you call structured airspaces. That means all those tracks I talked about before in the beginning, they're all applicable here. So what's the difference between structured and unstructured? In rural areas especially, you can't create all this infrastructure. So remember, whenever you have a lane, or this, let's call this a corridor or a lane, then you are building the infrastructure below on the ground. Say, for example, where do you want to put the cell towers, especially new communication base stations, specifically for drones? You are installing them on the ground, just below the air corridor. The other kind of equipment is weather stations. Weather is going to play a very, very big role. In fact, in Dallas-Fort Worth area and in my university also, a couple of companies are installing what they call micro weather stations. So the importance is that the global weather information is not sufficient for air traffic management for drones or for AAM vehicles. So we need to have more precise local weather. So we call that as micro weather station. Even more interestingly, there are efforts to install weather stations on the drones so that you are getting more realistic information, more precise and localized information. So imagine that every vehicle has weather station on the vehicle. Then all this data could be communicated to the ground, and then we need to develop measures to aggregate all this information and again use this information to pass it on to vehicles which are about to enter those regions. So air corridors are meaningful, and then it will facilitate or making implementation of this infrastructure. It becomes more affordable. Whereas in rural areas, you cannot build all these facilities. So there we use something called a geofence concept. A geofence is a bubble around the vehicle, and it is not dynamic. When the vehicle moves, obviously the bubble also moves along with that. So the key concept is, key idea over there is every vehicle is making sure that nobody enters its own geofence. So geofence concept also is very, very, very well received by the community. So geofence is more meaningful for rural areas, in my opinion. And then this kind of structured airspaces like cells, lanes, these are more meaningful in the urban area. So both have their pros and cons. So some people say, why do we want all these structures? Why can't we just freely fly? But again, the answer is, if you have this predefined or well-defined structures, then the infrastructure design or investment will be much more efficient. So merging is one case where one vehicle which is currently in one lane, it needs to go into other lane. Then here is an example of this rural areas I was talking about. We call that as a crossroads. So look at the scenario here. The two vehicles are coming from different directions, and then they predict potentially they may come to the same location in the next few minutes or few seconds. So that's based on the prediction, or given that now remote ID is popular, remote ID is already a rule. Remember, remote ID it means that every vehicle is going to send its location. It's just one way broadcast. So you could piggyback on that. You are getting the messages from the other vehicles in the neighborhood. So based on the data you get, you can predict where the vehicle is going. but obviously this is more accurate compared to predicting through other means, because you're getting the real data. You know where the vehicle is and where it is heading. So make the prediction and then try to resolve the conflict. So once again, the key idea is both for merging and even these crossroads concepts, we're trying to see what information we need to share so that we can avoid the potential collision. So another thing that we need to keep in mind here is, here we are assuming these are cooperative vehicles. So if the vehicles are cooperative, yeah, well and good. You are getting information, at least initial information from the vehicles, or you could use that location information coming from through the messages as a means to predict and then refine. For example, if you have beam forming and beam steering capabilities, then you can make it even more accurate. You can predict the location more accurately and then try to communicate. And ultimately, our goal is through messages, we want to avoid any potential collision. So what if the other vehicle is not cooperating? So that becomes the same problem of collision avoidance that between two cooperative vehicles becomes what we call detect and avoid in the second case. If one vehicle is not cooperating, that means maybe something failed. Maybe its sensors failed, communication equipment failed, or maybe it is legitimately or it's not supposed to be in the air. Maybe it is intentionally not communicating. So in those cases, it becomes a detect and avoid problem. So that's an interesting thing you see. Collision avoidance between cooperative vehicles becomes a detect and avoid problem in the other case, if one vehicle is not cooperating. All right. The other thing is minimum separation. So this is called minimum airborne separation. So once again, all these use cases are coming from RTCA. RTCA had a meeting, and I believe they took a poll in one of the live meetings, face-to-face meetings. They asked them, what are the primary use cases you can think of? And then from the poll, they came up with these 5 use cases. And we took from IEEE point of view, we took those use cases and then built on them. So we went very far actually. RTCA stopped working, or rather took a break, but IEEE went too deep into these 5 use cases, and we are able to come up with what you call complete messaging and the protocol and all that, and it's ready to be released. So minimum separation is a concept where vehicles have to maintain minimum distance. So once again, things become easier when the vehicles are flying in the lanes. So structured airspaces are meaningful, and they provide make it simple actually. So in this case, what we realized is you don't need to send any messages. That remote ID that we talked about, in which each vehicle is broadcasting its location, heading, and all that. That information alone is sufficient to maintain the separation. For example, if the first vehicle is slowing down, then you know that the vehicle is slowing down. So the following vehicle will actually slow down as well to maintain the distance. The question about how much distance is required, all those things, like still in debate. We don't know yet. However, I think the concept of air cell also is very meaningful here. For example, you can say, let's maintain 1 air cell gap between the vehicles. And you can, in terms of automation, this kind of ideas are very meaningful. Concepts will come very handy, because if the weather is rough, make it 2, or only have 1 lane instead of 2 lanes, 2 adjacent lanes. So all these things could come very handy with structured airspaces if we build it right, if we do it right. Okay, the next use case is called collaborative sensing. So collaborative sensing is very useful when there are like in the case of detect and avoid or identifying any hazards. So the key idea here is a vehicle can only see some portion of the airspace hazard. So we want to aggregate the information coming from different airplanes, different vehicles, and come up with the overall scope. So one thing that that is done by the industry is the industry defined how to describe the airspace hazard. So the organization called ASTM defined something called constraint. They call that as a constraint. A constraint is like a no-fly zone. In fact, you can say it could be no-fly zone, or it could be the constraint. Constraint can also be seen as a operational volume. So let me explain that a little bit more. A constraint is a geographical volume or 3D volume that ASTM defined as a regular structure, like a cylinder, for example, or a 3D structure where the ceiling and the floor are the same polygon. You know, for example, let's say the one kind of 3D structure is, imagine that the roof and ceiling have exactly identical. So then all that you need is describe the polygon, one polygon, and then give the lower altitude and higher altitude. And with that, the description becomes very simple. So that kind of definition is already existing in the industry. So the point here is that every drone or every vehicle will describe its own volume or its own constraint as it perceives. You know, for example, if there is a rogue drone going randomly, then I think we need to aggregate the information coming from all the drones, and obviously we need to inform that to the ground control, which can aggregate the information. So ultimately, what we are defining is defining airspace hazard as a structure or a geometry in the airspace, and that information can be passed on to all the vehicles so that they can avoid. So these and I'm trying to describe them as succinctly as possible. But if things are not clear, I'll be very happy to share more information with you later. And then another important use case is called airborne rerouting. So what is the idea here? The ground control is, in the beginning, created a flight plan, and the vehicle is going as planned. But suddenly there is a rough weather or some no-fly zone or traffic congestion happen. So we need to inform the drone to take an alternate route. In fact, there are many reasons actually, and this is very common too. Flights can take even though they have a plan, they may have to change the route for a variety of reasons. For example, the landing airport or vertiport may not have space, or there is a lot of congestion for some reason, or some public event or some emergency event occurred on the ground. So in all those cases, we need to provide a dynamic or a new route. So this is called airborne rerouting. By the way, a route is very well defined again by the industry. It consists of sort of waypoints. Each waypoint has lat-long altitude and also the expected time of arrival. So those are all well defined, and they are being used by both UTM and AAM folks. And in fact, I feel like that kind of information, we won't get it in the literature. I haven't found a good paper that describes all this. Because of our engagement with the industry on the standards, we're able to get that. So the flight path is, initially there is a flight plan and it has to be changed. So what happens? The operator, ultimately the operator of the vehicle is responsible. When I say operator, it's like there will be a human being there, and then you have, of course, a bunch of tools to plan the route. So the new route has to be defined ultimately by the operator, with help from the some other traffic management subsystem, or even the drone. The vehicle might itself provide, oh, I see something and I need to avoid, give me the new route. So two things have to be kept in mind. One is, if the vehicle is within the radio line of sight, obviously it can talk to the ground control station. If not, the ground control station has to use another drone as a relay to pass the information. So once again, you see the need for V2V and the nature of immediate response, and low latency communication. So these things cannot happen, especially when the density of vehicles is high or large. We must have V2V, and without V2V, we cannot really address these use cases. Okay, so here is another scenario where it's almost similar to the previous one. It's rerouting, but in this case, it doesn't have to be a route information. It could be anything. Maybe you found some information like sensor information. So one vehicle may have cameras, and other vehicle might have a lidar. So you need to share information that you are collecting from different sensors. So in this case also, it is very meaningful to have V2V communication. So what is the end goal? The end goal is to have a fully automated airspace. So this is the same picture that I was showing before. How do we communicate effectively? How do we communicate efficiently? How do we share the airspace between UTM vehicles, AAM vehicles, commercial vehicles, helicopters, and others? So that is a key point. And automation is necessary. In fact, at the same time, it is important to have a human in the loop for safety point of view, but most of the things should be automated. Basically, we do everything. We do everything as efficiently as possible, sharing the resources, sharing the airspace. And in this context, autonomy is important, but to facilitate autonomy, you need to have V2V communications, air-to-ground communication. So communication support is essential. In fact, I think we need sensors, computation, or computing elements, then communications. All these things they work hand in hand, I believe. So automation is not a different concept, is not a separate concept, but it depends on other factors: computation, communication, dynamics, controls, and all that. So one thing that I didn't really talk about is the need for digital twins. You can see, if you are working in that field, NASA actually released the software for what they call generalized eVTOL. I think just few days back, I already downloaded the code, and my student has been doing some simulations. So that's my big picture talk. I know that these talks are intentionally made, kept at high level, so that each one of us can see where exactly we can contribute, and then we can. My one other goal that I have is to have a collaboration with those who are working in this field. For example, one of the fundamental project that I'm working on is channel modeling. Vehicle to vehicle communications, we need to do air-to-air channel modeling. Most of the research papers assume free space, but it's not. Even at 4,000 feet, there is still loss from interference, noise and interference as well. So the path loss model had to be more accurate. And for different scenarios, urban scenarios is different, suburban is different. There are some research papers, but then more work needs to be done in that direction, in that dimension. Same way, handover management, interference management, all those things have to be require more attention in the literature. So I'll stop here and then take up questions.
Thank you very much, Professor. If people would like to ask questions, please raise your hand. I've lost control of my computer, so Professor, could you have a look to see who's asking questions?
Sure. Yeah.
While people are thinking, I might just ask a very quick one. It seems to me like if you're going to optimize a very busy airspace, you might need to have helper drones that either use radar or have a kind of air traffic control role. Is that too simple a concept, or is it something that is not envisaged and everything is autonomous?
Actually, the what I know is that in recent discussions with NASA, in fact, there was a meeting that NASA called asking the public safety folks to join. Interestingly, the public safety folks have their own obviously they need for sending drones for emergency situations and other crime prevention and all that. So the radar is necessary actually. We need to make sure that that airspace is clear, especially in emergency scenarios. So there is a need to look at, for example, how much range we need. So that support has to come from the companies. So the another dimension is and that ATC is not going to, literally speaking, do anything. In fact, they only provide the supervision and the guidance. But in terms of traffic management, the private entities have to manage themselves. So which means that there should be that infrastructure, including radar and communication, all that support, weather stations, all those things have to come from the industry only. So while there is a interaction with the ATC, but it's not expected that ATC is going to provide the services. Did I answer the question?
Thank you. Yes, indeed. Are there more questions?
Yeah, there is one in the chat.
Yep.
That's about the collision detection. Pretty, in fact, that is interesting. That is active topic and active research topic. So in my own way, my students actually submitted a paper to Advanced Air Mobility Symposium that is going to happen in Montreal. Some of you may be aware of that. It's in September, I believe, in Montreal. So we divided this collision and detection into 4 scenarios. One is structured and unstructured spaces, then cooperative and non-cooperative. I hope it is meaningful. So it's like cooperative vehicles in structured airspaces, cooperative vehicles in unstructured airspaces, non-cooperative vehicles in structured and non-cooperative and unstructured. So that's how we divide it. And it is a hot topic, and the challenge is, as opposed to commercial aircraft, here you have to assume the density of the vehicles is going to be high, and the need for quick action is important. So it is a good topic, and I'll be more than happy to. I'll be glad to connect with you, and then discuss potential opportunities of collaboration.
Are there any more questions?
Yeah, this is the only question I have.
That's the only question. Does anybody want to ask another question? We're a little bit over time, but if there are no more questions, then I'll wrap it up.
Yeah, there's one more, I think. What are the in-vehicle sensors for UAV we can use to detect 360 degrees of object detection? Yeah, this is actually interesting.
I was going to ask a question. When you said put up your hand, I literally took that to mean I put up my hand.
Okay.
Yeah.
Yes, sir.
My question is, at the moment we see very large numbers of uninhabited vehicles, drones, which have entirely the opposite intention, i.e. military applications in Ukraine, in Russia. So my comment is all these protocols are only applicable if areas, countries even, cooperate with each other. So are any of these protocols applicable to some military applications?
Actually, this is entirely this work is focused more on the civilian side only. Even though there are ongoing projects from defense perspective, because obviously defense industry is putting a lot of funding in, like, for example, swarm operations. But this project, Advanced Air Mobility project, is solely focused on civilian applications.
Right. Thank you. I do.
Yeah. Yeah. In fact, probably the other way, we will, based on the defense applications, we may get some, like, for example, sensors, sensor technology, like for, one good example is GPS. I had some experience where we were trying to use, but GPS denied navigation. How do we navigate when the drone's GPS is not working or GPS signal is not coming? So what's interesting is, if you try to use IMU sensors, there is a way we can estimate the location based on the previous known location. And so I was reaching out to some companies, how come I am not able to get a good accurate estimation with the IMU sensor? They said in the military level, in the military side, they use multiple GPS sensors, for example, multiple IMU sensors. So you need to have more and more, maybe expensive, but more accurate IMU sensors to be able to address this GPS denied navigation. So my point is that it is the defense applications which give rise to probably more sensors or more ideas that we can use in the civilian side.
Right.
I hope I answered the question.
Thank you. Just one other comment. You mentioned it's in communication between vehicles when you're beyond the radio line of sight. You need a third vehicle to relay the information from one to the other, which seems rather problematical. Wouldn't a satellite communication system be more practical?
You're right in the sense, especially if you can't find a relay node, like rural areas, you may not be able to find a relay node. So in that case, satellite is the best option. Here we are assuming that there are enough vehicles, and even though there is a relay, it could be still faster than or low latency compared to satellite communication. So here, the assumption is that even there is a multi-hop communication, still it is better than the satellite link. That's the case. At least, we still have to do probably more testing to verify this hypothesis. But the satellite, at this point, the delay in satellite links is still larger.
Right.
But it could be complement. The other option is, other way to look at is, if this doesn't work, you go for the satellite. Or if satellite communication is delays in satellite link is high, then we should go for even multi-hop communication.
Right.
Yeah.
Thank you.
Okay.
In the chat, actually, there's one last thing I wanted to comment.
Go right ahead.
It is like about the in-vehicle sensors and UAVs. It is it's a kind of very critical to have lots of sensors. In fact, there is something called vehicle health management, especially the structural integrity or integrity of the structure of the vehicle. One thing that I have a use case, I have as an application or example where, suppose a bird hits the plane and something is damaged. Then that has to be detected as quickly as possible. So we need lots of in-vehicle sensors, almost like embedded sensors on the structure, and everywhere possible. Everything has to be through sensors only. In the scenario when I described, suppose the structure is damaged, then if there is a pilot, he or she will be able to see or sense that the damage. For example, when you are driving, if the tire is punctured, you can sense it. But if in the case of autonomous vehicle, that becomes very crucial, and we need to make an immediate decision whether to abort the mission on land or continue. So in those cases, there is a need for including or installing, embedding as many sensors as possible within the scope of size and weight of the payload. But in terms of, I think primarily in terms of answering this question, what kind of sensors? I think the structural integrity sensing sensors are very critical.
Professor Namuduri, thank you very much. I think we'll wrap it up now, and if people want to follow up with you directly, that would be very, very good. In just concluding and thanking you, the very, very impressive thing I think that your talk brought out was the multi-dimensional nature of air mobility and vehicular communications, everything from spectrum through to, well, I guess structural integrity and navigation and all the rest of it. It seems like an immensely fertile field, and one that allows for or creates wonderful opportunities for collaboration. So I'd like to congratulate you on an excellent talk, and thank you very, very much from the Victorian VTS and ComSoc chapters. Very much appreciated. Thank you.
Thank you very much, and have a wonderful rest of the evening. Thank you.
And I'll thank our participants.